session of Young Researchers Meeting. This is a session of theoretical physics. We have two speakers, and the first one is Marcio Di Vece, and he will talk about the characteristic of water model and invasion process in city configuration.
So, thanks everybody for coming in, and I will talk. My name is Marcio Di Vece, and I will talk about water model and invasion process. These are models in opinion formation. That is a new field that started in 2000 from statistical physics, and that tried to describe human behavior and the formation of an opinion in a community. So, my work, I will tell you about my work. Then I dealt for my master thesis with the Professor Federico Corbello at the University of Salerno and Dr Castellano from the ICS of the Siena at Rome. So, briefly, I will talk about consensus models. There are models where there are a lot of agents that are, for example, individuals, and they exchange ideas with their friends in order to reach a consensus state. There is a state where every person has the same idea. And then I will talk about Sueta's theory, that is the known theory for consensus models that I will describe later, and its limits, and a theoretical approach that I developed in order to describe these models beyond the range of validity of the Sueta's theory. So let's start. What are consensus models? In consensus models, we have actors that are situated on nodes and that influence each other following a stochastic rule. The thing is that consensus is not a result of a phase transition like is a model, but is the result of repetitive social interactions. So let's go and talk about the most simplistic ones that are the water model and invasion process. So let's see. In water model invasion process, the opinion is a binary variable. So, for example, it can be -1 and +1, like is a model, or it can be 0 and 1. For example, this happy person has a state 1, and these sad ones have a state 0. In the water model, there is this stochastic rule. The first chosen row is picked randomly, and then you see its neighbors, its friends, and this node switches opinion and take the opinion of one of the others. For the invasion process, instead, the first chosen node invades, exports a state towards one of its neighbors. So, in our processes, we will talk about C configuration. It is a configuration which there is only a single actor with opinion 1. So it's like there is unanimity at the start, and then you put another with another idea, and what you are searching for is the probability to reach consensus of the idea 1 from one single node. So the opinions can have the same strength, or you, and in this case you have like a diffusive process, or you can add a bias. There is like a net flux or a drift that induces a difference in symmetry and asymmetry in the opinions. For example, we can introduce in a certain way S equals 0, where the opinion I have the same way for S equals 0, or S more than 1. That means that opinion 1 is more powerful than opinion 0. And that can happen because maybe opinion 1 is better assimilated, for example, Salvini. Yeah. And the presence of bias changes the dynamical equations and the solutions. and the solution. So it is very interesting to see the effect of bias in the models. But okay, but your model is a very simplistic one. You take one node and then it takes or exports its state to one another. And you think about this, is this realistic? The thing is that with a simple modification of the voter model, one can explain elections like the USA elections from the 2000 to the 2012. For example, here is a graph of the fluctuation of the vote share between counties or congressional districts or states. It can be done for district type of sections. And there is a good result. And for the correlations of vote shares, depending on the geographical distance, they see a power law, and they predict a power law, and they see it. So, and this work is made by Garcia et al. From IFISC, and is posted in a physical review lecture. So, let's go on. Okay, we could put our models on a square lattice or a ring chain, but it is not so useful because we want to simulate social context. And for social context, we need a structure, a mathematical structure that resembles social networks. And these are the networks, obviously, when there are a lot of nodes, as you can see by the circles, and edges, as you can see by the line that connects them. So networks are made of nodes, as I said, edges, and can be described by an adjacency matrix, where adjacency matrix can have values 0, 1. For example, the element A, I, J is 1 because those nodes are connected, but A, I, K is 0 because they are not connected. And then we have topological measures like the degree is, for example, for E, the number of its friends, that is 3, or the average neighbor's degree K and N, that is the average of the degrees of its first neighbors, as the name says. And then the eigenvector centrality, that is another measure, and that is evaluated by an eigenvalue problem very easily. And now, we will talk about the scale-free network. The scale-free network is, it is proved that it can well describe social networks like Twitter. In the scale-free, we have an high heterogeneity of degree because there is the coexistence of hubs, like, for example, if you think about airports, you can think about Malpensa or Linate, and peripheral nodes that are not well connected. The scale-free is described with a distribution of degree that is like a power law, and as I said, has a high degree heterogeneity. So now we talk about search theory. In search theory, we use certain approximation. For example, the Aniel approximation that briefly means that I take the adjacency matrix, and I have 0, 1, and I substitute to it its ensemble average with a lot of scale-free, and then I take the average, and for example, the element ij depends on the product of ki and kj, and not other topological measures. And the results of the search theory, the dominant results are that the consensus one probability, that is our quantity of interest, depends only on the degrees of the nodes and not other topological measures. And then that the dynamical equation can be solved for s equals 0, then unbiased case, and for s less than 1. So in unbiased case, if we start with a single node with opinion 1 and degree k, we see that for the Bottom model, the consensus one probability depends on the degree of the first node with opinion 1. And for the inversion process, we have a dependence on the inverse of its degree. What we've done is numerically check first these results. And what we see from numerical simulation for a scale-free of an uncorrelated scale-free of f equals 100, we see perfect agreement. This is a pre-study of ours. And for the invasion process, it's the same. And we see that the standard deviation follows the central limit theorem, as we can see from the beta equals -0.5 and this behind it. Then for s less than 1, we can see that the dynamical equation can be resembled those of a random walk. It can be easily solved and have this form where omega is a sort of weighted magnetization. But let's go over and see that we find perfect agreement. So this is only a first study for the check for the theory. Then now the thing we are interested in is what happens when the bias is so high that is outside the range of validity of this theory. Both for the bias bottom model and the bias invasion process, we don't have agreement as we could think. So for example, s equals 2, s equals 3, s equals 5, s equals 8. And what we questioned about was why doesn't it work? As we can see in the standard deviation, what we plot here is the consensus 1 probability at fixed degree of the first node that should be the same for the search theory. And we see that there is a standard deviation that doesn't go to 0. Then there is some other measure that there is another measure inside the consensus 1 probability, and we want to find it. So we try to find correlation between consensus 1 probability and the average degree of the neighbors of the first node in state 1. And we see that for s equals 0.01, we have a flat behavior, as we could think about. This is a value in the Sud et al.'s theory regime. For s equals 3, we find anticorrelations. So it is dependent on these topological measures. So if we go to invasion process, we find the same. But instead of an anticorrelation, we see a correlation. So it must depend on this topological measure. If we go for eigenvector centrality, we find the same thing. First anticorrelation and then correlation. So we could think that the consensus probability must depend both on average neighbors degree and eigenvector centrality. Another thing is how does the distribution of time change when I have a higher bias? What we see is that when I have a higher bias, what happens? That the opinion 1 is stronger. Then you can think I develop consensus 1 easier. The thing is that, but easier or faster? And what we can see here, this is the condition distribution of reaching consensus 1, given that I reach consensus. Then from a time of about 100, we can see that we pass from a configuration where we reach consensus 0 to a configuration where we reach consensus 1 with probability about 1. For s equals 3, this time goes from 100 to 9, 8. So I reach consensus faster. But and this time is in Monte Carlo steps, obviously. I reach consensus faster, but I reach it faster, but in less moves. Yeah, this is the minimum number of moves to reach consensus given s, and we can see that increasing s, this minimum number of moves decreases. So we think, okay, but if increasing the bias, I decrease the number of moves that I need to reach consensus 1, is it that the first interaction are very important in this process? And so we develop a theoretical approach. In our process, it is made so that we can reach or consensus 1 or consensus 0. There are not other steady states. So trying to find consensus 1 is like trying to find the probability of consensus 0. How can we reach consensus 0? for example, you can think, okay, there is one node in state 1, and he can communicate with others. But, for example, the first thing that can happen is that it communicates with others and change its opinion, and then I have consensus 0, okay? Because I started with a single with opinion 1. Or I can export in a certain way the opinion 1 to another, and then the other change mind, and the first change mind, and I have consensus 0. It can happen in a lot of ways. And this is described by this formula. This is the probability to reach consensus 0 with a number, n max is the number of nodes in opinion 1 during the process. So, okay, but the thing is that, for example, if we want to calculate this probability, it is very bothersome, and we have to approximate. For example, at the first terms of this sum. Okay. So what we do is in this presentation we will talk only about the first order approximation. This is the approximation in the first move. For example, the consensus 0, in our opinion, for the following, will be reached only with the first interaction. So, for example, at the first order I have this probability to reach 0, given that only one node is in the whole process is in state 1, plus consensus 1. And then probability of having consensus 1 at the first order is the probability of having the first interaction that gets the one to the friend, the opinion 1 to the friend. It's like I talk with one of the audience and say, my opinion is wonderful. And he said, okay, it's very good. And then I have consensus in the whole chamber. Okay, this is the approximation that I'm doing. And if I apply this to the models, I see that there is this form for the bottom model innovation process, where K is the degree of the first with the opinion 1, and Kj is the degree of the first with which it interacts. Okay? And I see that there is a sort of anti-correlation for the bottom model, as I saw here. And there is a sort of correlation with Kj that I saw here. Where here I thought about Kn as substitute of Kj. So I apply it to the bottom model, and I see that increasing hats, my numerical data follow this master curve. This is the theoretical curve for the first order approximation. And it really is fit well for s equals 8 and s equals 5, but mostly for s equals 8, as you can see from the blue. And then I applied for the innovation process, and I see something bad. It is like, okay, follow a little for s equals 8, but not for the other ones. But I want to compare my results with the theoretical curves by Sudethal's theory. So what I have to do is marginalization in order to get down the dependency on Kj using this probability. It is the degree distribution of the first neighbors. And what I see is that Sudethal's theory is very bad, as I said. And for the first order, I get perfect agreement for s equals 8, and a good agreement for s equals 5, and not a good for s equals 2 and s equals 3. And for the innovation process, as you can see here, first order I get a good fitting for both s equals 8 and s equals 5. So, conclusions. What we did is confirm the Sudethal's theory for unbiased and s less than 1 bias models. Then we saw correlations when increasing by the bias between the consensus 1 probability and other topological measures. And then we saw agreement between the numerical data and our theoretical approach for higher S. The problem is that it is very difficult to compute the second order and beyond. But we are doing it. So check on us. Thanks for your attention.
Thank you for your interesting contribution. Any question?
Magari urlo. Thanks for the talk, and I'm really curious about the actual application of some sort of models to real scenarios. And the only data you showed was in one of the first slides, right? And I don't know if you can elaborate on them a little bit, because I didn't get really the point of this slide, and I think that's an important point, no?
Yeah, the thing is that before 2014, they thought that the voter model and inversion process were toy models, only to describe a certain type of dynamics. But in the 2014, they found that a certain modification of the voter model, when we add geographical distance, we add the recurrence of influencing people in your home or in your workplace, can extract these, for example, these statistics. What is this?
Yeah.
This is the distribution of the vote share. So the votants, but is the distribution of the fluctuations. This is V minus the mean of V. V is the vote share, so it's like the voters that have a certain opinion. There is like, here was +1 or -1, and this is +1. And so it is well fit by Gaussian. But it was not so trivial, because what they did is, okay, we take data sets from 2000 elections. What they did is this. They got the 2000 data sets, they put there, and then they see, okay, let's do the dynamics and see what happens. And they found very well results for the election of 2000, and then till the 2012. So for 12 years, they found agreement with the curves.
So, but not with the model you just explained, but with
a modification.
More elaborate one.
Yeah, the model is
so the Gaussian is okay.
The model is the prerequisite, and then you have to add things. But in order to develop these models, or to understand these models, you need to understand before the toy models.
Yeah.
So you can develop on it. There are other models, like voter model with other features. So it gets complicated there.
Yeah.
Other question? So if there are no more questions, let's thank the speaker again. The next speaker is Luciano Pedrosiello, and he will talk about the rule of neutrino mixing in accelerated proton decay. Okay, we are ready.
So, okay. Hello everyone. I am Luciano Pedrosiello, and I'm the person between you and the end of the conference, so I'll try not to bother you too much. The title of my work, of the work I'm gonna talk about is Lo so, ma. Okay, I prefer this configuration. Okay, it is a rule of neutrino mixing in accelerated proton decay. work in collaboration with Blasone, Lambiase, and Luciano. No, okay, it's fine. So, first of all, a brief outline. I'm going to explain why it is important to study such a phenomenon. Then I'm going to spend just a couple of words on the preliminary tools needed for a better comprehension of this phenomenon. After that, there's going to be an historical excursus on the inverse beta decay, followed by the introduction of neutrino missing in the context of the inverse beta decay, and after that, conclusions and outlook. So, first of all, why it is important to study such a phenomenon? It is important because, first of all, we can test the consistency of quantum field theory in covered background through the comparison of the decay rate, both in the inertial frame and in the moving frame. And this has been proved to be a theoretical check of the Unruh effect. Another point is the clarification of some conceptual problems related to the introduction of mixed neutrinos in the inverse beta decay, as it has been shown in this paper. And then, last but not least, is the investigation of the issue of mass or flavor neutrino states as fundamental objects in quantum field theory, which is, by the way, still an open issue. So, first of all, I'm going to tell you what is, in four words, what is the Unruh effect. Okay, this is the Minkowski spacetime, and it is well known that in order to describe to best describe the observer which moves on a word line with uniform acceleration of uniform accelerating observer on this word line, Ringler coordinates are more useful than Minkowski ones. But in doing so, we know that the uniform accelerated observer sees these hypersurfaces as horizons. And physically, it means that the real observer perceives the Minkowski vacuum as a thermal bath of particles. So this is just a thermal distribution, where the temperature of this thermal distribution is proportional to the acceleration, and this is called the Fueling-Davis-Unruh temperature. That's it for what I need to say later. Then we're going to also use the first formulation of mixing transformation made by Pontecorvo, which relates the definite flavor neutrino states to the definite mass ones by means of this rotation, because basically we're going to consider a simplified two-flavor model, and these formulas can lead to the quantum mechanical oscillation probability given in this expression. So, after having said that, we can begin with the core of the talk. And it's important to state that in this article, Müller was the first one who stated that the decay properties of particles are less fundamental than commonly thought. In fact, if you consider the proton, it is known that its mean proton lifetime is greater than 10 to the 28 years. But if the proton now accelerates, we can see that this process, which is called the inverse beta decay, is not kinematically forbidden, so it basically can take place. And this means that the lifetime of particles is not an absolute concept. So, from the point of view of the inertial observer, of course, this is what happens. The accelerated proton at a certain point decays into an electronic neutrino, a neutron and a positron. But what happens now from the point of view of the co-moving observer, where the proton is at rest? Of course, thanks to the Unruh effect, it sees a thermal bath of electrons and neutrinos and the respective antiparticles. And so, basically, the proton in the co-moving frame can decay according to one of these three channels. So, after having said that, the first calculations in this direction were performed in this article, in these physical review letters, in 2 dimensions and for the case of massless neutrino, in the hypothesis in which the acceleration is less smaller than the masses of the vector gauge bosons. In this approximation, what we can see is that we can, of course, consider the Fermi current-current interaction, given here in this expression, where neutrinos and electrons are treated as fermionic fields, while proton and neutron, so the hadronic section, is considered basically as a two-level system, where the neutron is an excited state and the proton is the ground state. And the current that is introduced in the action is this semi-classical current with this effective Fermi action. So, of course, now we have only to compute the decay rates in both frames, reference frames. So here we have the field expansion for the fermionic field in Minkowski spacetime, usual procedures. And then what now we need to compute is the three-level transition amplitude, which is given in this expression, very simply, and the differential transition rate, which is directly related to the physical quantity that we need to compute, which is the three-level decay rate. And if we perform calculation, this is the expression that is obtained in that paper, where here with the tilde indicates that there is a division for the acceleration. And this is the modified Bessel function of the second kind, which has been tormenting me for months. But okay, never mind. So when it comes to comoving frame calculations, we have to perform the field expansion here, which of course will be different and more complicated. And we have to follow basically the same procedures, with the only difference that when it comes to the evaluation of the differential transition rate, for each process, we have to attach to the absorbed and emitted part, which is here. It can be either electrons or neutrinos or respective antiparticles, the right fermionic thermal contribution, which is given here. And then we can compute all the differential transition rate for each of the channels that I showed you before in the common frame. So after doing that, one is to sum up all the three contributions of the decay rate channels, and we're left with this expression, this final expression for the decay rate in the moving frame. So what can be seen, what can be shown is that at three levels, these two decay rates perfectly match. In fact, here in this plot, there is on the logarithmic scale the mean prober lifetime, which is the inverse of the three-level decay rate that has been evaluated before, as a function of the acceleration. And this is the plot both for the inertial and the moving frame. And basically, this proves two things: that the Unruh effect is mandatory in quantum field theory in curvature background, and that, of course, the QFT in curvature background satisfies the general covariance because it is built as a general covariant theory. Okay, I'm going to skip this part because here basically there is another work which generalized this discussion to 4 dimensions, and in the case of massive neutrinos. And basically here they prove that thanks to some mathematical identities, the equality between the two decay rates can be proved not only by the plot that I showed you before, but also analytically. And can be obtained this nice expression, which is equal in both frames. But now the point is, how does neutrino mixing can be inserted in this context? Basically, it was done the first time in this paper, but the point here says that the two decay rates do not agree anymore. The point is that the authors of this paper said that the neutrino state violates the Kubo-Martin-Swinger definition of a thermal state, so basically spoiling the thermality of the Unruh effect. And then they conclude saying that the contradiction must be solved experimentally, because they obtain two different results for the mean proper lifetime of the problem. But of course, as a theoretical physicist, no experiment can solve a theoretical paradox and inconsistency of a theory. So, in a certain sense, we, in the paper that we published, we wanted to preserve the general covariance of the theory, even when the neutrino mixing is introduced in the context. And just a word on this, after the publication of our paper, there was also another paper that tried to solve these ambiguities, but we are currently working to point out some inconsistency of the approach of this paper. And in fact, we're still working on it, but I hope we will do it as soon as possible. So, after having said that, of course, the procedures are always the same. And so basically what we can do is now introduce the neutrino mixing in context and perform the calculations that I already showed you before. Here we have performed this in 4 dimensions and for massive neutrino, of course, otherwise there is no mixing. We then evaluate the 3-level transition amplitude, where these contributions are, this expression are these integrals, more or less complicated. And then we are left with these results for the three-level decay rate in the inertial frame, where let me call these terms the diagonal part, and this one the off-diagonal contribution. And now we had to evaluate this three-level decay rate in the commuting frame. But a little digression before that, and let us try to do what Al-Wali et al. In the first papers did. So we consider in the moving frame the mass eigenstates to be the asymptotic neutrino states. And if we do these calculations and we evaluate the three-level transition rate for each decay rate channel, here I've reported only the one for the first process in the moving frame, we are left with this expression in the moving frame, where we can clearly see by the comparison, okay, this is the unawkward expression, which is the diagonal part of this three-level decay rate in the moving frame. But the most important thing is that the comparison between these two decay rates shows that although the diagonal parts are equal, the point is that first of all, Pontecorvo matrix elements appear with different powers, and moreover, in the moving frame there is no off-diagonal part. So it basically says that neutrino asymptotic states must inevitably favor eigenstates. The point is that, as I already remarked before, and as Al-Walia point out more than once in their article, is that this allows for non-thermal contributions of the Uru effect. And the point is that this is basically true. So they're trying to avoid it, but to tell the truth, there is a non-thermal contribution to the Uru effect, because when we consider neutrino mixing in accelerated frames, basically there are two Bogoliubov transformations that occur. The first one is the thermal Bogoliubov transformation that relates the field expansion in the Ringler frame to the field expansion in Minkowski frame. And the other one is the mixing Bogoliubov, which relates the fields with definite mass with the fields with definite flavor. And the point is that these two Bogoliubov transformations combine non-trivially, and the outcome of this paper made by my collaborators lead to this expression for the Uru spectrum, where we see that the first part is the usual Uru thermal spectrum, and this other part is the non-thermal mixing correction, which depends on the mixing angle theta and on the small neutrino mass difference, which is the approximation they did in order to obtain this first contribution explicitly. So the most important thing here is that non-thermal correction only appears at orders higher than that time over M, and this is going to be useful later. So now here is the calculation that we have performed in our paper. So going back to the comoving frame, we can use the fact that now neutrino asymptotic states must be flavor eigenstates, and we perform calculations according to the usual procedure, and we reach this expression, this final expression for the decay rate in the comoving frame at free level, where here is the off-diagonal contribution. Quite ugly in my opinion. Okay, yeah. And but now, thanks to this comparison between the two decay rates, we clearly see that the diagonal part, of course, is already fixed, and the Pontecorvo matrix elements appear with the right power. But now we have to check whether these two diagonal contributions match or not. So, unfortunately, the evaluation of the storms is highly non-trivial, but we can say something in the regime in which we consider small neutrino mass difference. Okay. So, we can perform this expansion, and basically there are still some problems related to this part at first order. But at this point we had to consider a suitable limit, which has to be taken basically as a purely mathematical meaning, which is this limit. And as I already said, of course, this limit has a purely mathematical meaning, not a physical one. But it's just to see whether, at least in this regime, the two decay rates match. And fortunately, the two rates in this return matches, and here is the expression. Of course, apart from this expression, I wanted to remark that we can perform calculation easily because, of course, we have stopped at the first order in the expansion of delta m over r. Otherwise, if we have done other calculations at higher orders, we would have to consider also the non-thermal contribution to the Unruh effect. But, okay, at first order, this is the result, and okay, we're fine with that. So basically, we have seen that the Unruh radiation is non-trivially modified in the context of flavor mixing, that the neutrino asymptotic states must inevitably favor against states in order to preserve the general covariance of the theory, and that in a suitable approximation, the one that I already showed you, the agreement between the two decades is restored. Now the point is, we have to go beyond this approximation, and basically two things can happen if we go beyond this approximation. The first thing is that the two decay rates perfectly match, and okay, we're fine with that because we have solved the paradox, the theoretical paradox by means of theoretical tools. But okay, we can also take into account the fact that the two decay rates cannot agree. So at this point we have to consider basically three options that can lead to the solution of this theoretical paradox. The first one is that neutrino mixing is at odds with general covariance, but we tend to exclude this hypothesis, but this is an agnostic view, but of course it is a possibility. Then the fact that the Unruh effect with neutrino mixing must be further revised, or maybe that Pontecorvo transformations are not consistent with quantum field theory, but instead they represent a quantum mechanical limit of a more general transformation. And of course, after having said that, there's nothing more to say. No, thanks for your attention, and ask but not too much because it's the end of the conference. Thank you.
Thank you for your interesting and funny contribution. Any question?
I have a super naive curiosity, maybe it's not even a first question, but yeah, you have to deal with a thermal bath of particles because of the Unruh effect. But what particles are? I mean, is a weighted mix of all possible particles allowed from the energy you have to do? I mean, it's, I don't know if...
okay, you're basically saying why are we choosing only electrons and neutrinos? Yeah, well, because basically their first paper, the authors were considering only the inverse beta decay. Of course, we know that if an accelerated proton can decay, probably this is not the only process that can occur. But if we are considering only this process, okay, so then in the thermal bath, if we consider proton and neutron as a two-level system, basically all the other particles contribute in the thermal bath. But only because they considered only this process as the only channel which the accelerated proton can decay.
Other question? So if there are no other questions, let's thank the speaker again. So this was the last talk of this meeting. Now we will announce the official winner of the badge game.
First of all, I will give the solution of the badge game, and is that I have associated to the letter A 1 and in alphabetic order until Z, that is 26. I have made the sum of the first four letters of the name, and this will give the atomic number of the element. For example, in case of my name Giulio, G correspond to 7, I to 9, U to 21, L to 12, and sum is 49. This gives the atomic number of indium. And do you know this? Giuliana Galati e Calvi con stella. It is a sort of collective contribution to the solution.
We made several tries all together and I just picked the right number.
And this is the wonderful prize.
Oh.
Just 2 minutes, and we're gonna start with the closing ceremony. Just